Perfect. Um, okay, welcome everyone. Happy Wednesday, and it's once again my distinct honor to welcome Anders Sandberg, Dr. Anders Sandberg, onto the stream. Now a newly minted fellow of Parks College, Oxford, the most recently created Oxford College, a graduate-only college that is going to be dedicated to some really fascinating topics. So, before we kind of dive into that, do you want to tell us a little bit about your new role?
Well, right now there is very little to tell because it's literally getting built as we speak. The building exists but needs to be refurbished and, of course, in on a typical British manner, asbestos removed and stuff like that done. And we are organizing what the college is going to be. So right now it's wonderful. We are fellows and have no students. So this is kind of academic dreamland in many ways. It's of course going to turn into more practical nightmare when we actually have applications and actually have to give our seminars. But right now we get to organize things and come up with ways of being interdisciplinary. How do you inspire graduate students at Oxford actually going between different disciplines and doing great stuff?
It sounds very cool. And is it the old Redcliffe Science Library building you'll be in?
Indeed. So it's kind of a good
Cool.
neighborhood between Keble College, the Rhodes Foundation, and of course the Natural History Museum. In the back, there is also a weird little octagonal building with a very steep roof, the Abbott's Kitchen, which is apparently the oldest existing chemistry lab in the UK.
Oh, very cool. Awesome. Well, you shall have to try to nab that as your office.
Yep.
Oh, that's awesome. Well, congratulations very much on that, Anders. And is this your first public appearance as a officially recognized fellow?
Yes, indeed. So I better behave myself.
Well, excellent. Bravo. So yeah, basically today I wanted to continue the conversation. So last time Anders was on, we were going to chat about finding alien civilizations, and then kind of go into colonizing the universe and why it might matter that we could bump into alien civilizations. But we got hung up on talking about alien civilizations, then gunk, and had a very interesting conversation about that. So today, instead, we will go back to the colonizing the universe part because I think that's a really fascinating topic and one that you know more about than a lot of people. I think it's fair to say that you're a world expert on the topic of reaching out into the stars and fulfilling our cosmic potential. So,
At least the later. I'm trying to write the relevant sections in my book right now, and I'm constantly astonished by all the hard work and clever engineering going into it. And I realize, wait a minute, who am I to come in here? There are generations of people at NASA who've been working very, very hard on it, and they're real engineers rather than some kind of mishmash like me. But my job is rather to take these pieces and try to see what is the picture that the puzzle actually depicts. Can we say something about that? And by the way, can I point out that's a corner piece? It's going there.
yeah, and I think that interdisciplinary approach is part of what Parks College is doing. I think it's part of what the FHI Future of Humanity Institute at Oxford has been doing for a while now, and I think there's a lot of value to it in that there's not a you've got NASA there sitting and looking at the astrophysics of it and the very nitty gritty technical details, and then you've got some more typical philosophers thinking about the implications of if we encounter alien life, but you haven't got a lot of people working on putting together all the different disciplines and merging it into a whole, which is kind of what you guys do.
Yeah, and sometimes you also realize interesting things by doing that. I've been working all day on a paper which is not related to this topic, but it's kind of in the intersection of philosophy of value and information physics. So I've been kind of reviewing various odd things about how many bits of information you can pack into space-time before it turns into a black hole. And then my co-author has been linking this up to conversation about what's the ultimate limits of how much value there could be in an economic or moral sense. And then we're trying to get this to work. And it's interesting because physics here seem to be putting interesting constraints on ethics, which is kind of not something philosophers normally bring up. And conversely, ethics is actually asking some very interesting questions about what is value, and how does value actually get represented in actual physical systems like humans or animals or machines that are valuing different things.
So we're talking about kind of all types of value there, from the value that like a bacterium might place on following a chemical gradient, up to the value that a super intelligent, super feeling agent might place on continuing life on Earth or something.
Something like that. So this began when Will MacAskill started a talk by pointing out that economic growth, if it just keeps on going 2% per year, you get to absurd results in a few 100,000 years. You get a world economy that's 10 to the power of 860 times the current world economy in a few 100,000 years. And at that point, he said, and that's absurd.
Hmm.
And I immediately started scribbling and calculating. And
Of
he
course
was
you
kind of
did.
noticing my reaction because I was starting to wonder, why is it absurd? Why can't you have that big economy? You can, of course, say, yeah, but you can't have that much stuff. But
Hmm.
much of economic value we have today is not stuff. Many of the most highly evaluated companies like Apple, the total amount of stuff they have is much smaller than many the companies that just make concrete or an iron. And we are not that impressed with those very material companies, yet we are willing to pay quite a lot for Apple stock, which is weird because it used to be a gilded piece of paper. Now it's a record in a database that says that I have X units of Apple stock. And I'm willing to pay quite a bit of money to get those stocks. That's really odd. So similarly, we might argue about what kinds of values there are. There is a certain value for me of having a mug with something drinkable in. But on the other hand, your life is worth way more. It's not like I would trade 10 million mugs of nice drink for your
Hmm.
life. You actually do have priority. So some values are kind of infinitely more valuable. They're lexically prior, as philosophers would put it in their jargon. But you can still do the value stuff. Because normally, if I'm asking which hand sanitizer is the best one, you're going to do an evaluation of some kind and say the left or the right one.
Hmm.
And that's really what a lot of value is about. You want to make choices. And typically, a human life is worth choosing in front of almost everything else. So we need to do rankings. And at this point, this is cognition. This is comparing pieces of information that we have stored. And oh, storing information, there are physical limits on that. I only have 1.4 liters of brain to store the stuff in, which means that there is a largest value I could possibly store in this brain. Now, that might turn out to be a very, very big value. It could be that just like human lives are, in some sense, infinitely far above normal economic values, maybe there are super values that are even better. So once we make super intelligent AIs with an exquisite grasp of ethics, they're going to point out some hierarchy of ever higher levels. But still, you need to represent it. Even that super AI needs to be able to reason about that super value and that hyper value. Which one is most important? Oh
Hmm.
dear, now I have a problematic choice here, but I need to choose hyper values over super values. So it all boils down to what can animals and humans and AIs represent? And that's set partially by physics. And at this point, of course, philosophers will start saying, yeah, that's a kind of boring constraint. Really, we're talking about more the fundamental principles, except that if ethics is done inside this universe, it's going to be always forced by that. And suddenly we're in a land of a very surprising issue of how physics and ethics interact. It's a little bit like Scott Aronson, who's a brilliant theoretical computer scientist, when he pointed out that the question, is information physical, is a quite profound philosophical and practical question.
Hmm.
And similarly, many questions in theoretical computer science actually do have philosophical implications that are pretty profound. So I love being in this kind of area, but We got rather far away from space now.
Yes, of course. So bringing it back around, I suppose. Um, if we are to ever achieve these kind of limits of value, we're probably going to need to get control over quite a lot more matter and energy than we currently have. Um, so I guess the first thing I want to talk about is how much is on offer, and assuming no alien civilizations are around, as we talked about last time, to get in our way or to provide massive ethical problems. Ignoring the whole we get wiped out in an alien genocide or we wipe out aliens in a horrible genocide sort of scenarios. Um, what is our cosmic endowment?
Yeah, and that depends a little bit on what actually is useful. So we are made out of baryonic matter. We're molecular structures composed of atoms that consist of electron, protons, and neutrons. And the protons and neutrons make up most of our mass. And this is a lovely form of matter because it can have complex chemistry. Uh, it's fairly solid, so it can channel energy. It's very, very useful, as we have kind of noticed as living beings and making technologies on the surface of Earth. And at first, we might say, yeah, actually, most baryonic matter isn't in a convenient form. Most of it that we can see in the sky is, of course, plasma. It's if in the form of hot stars where you can't do any chemistry. Um, but between them, about a millionth of the mass is in the form of planets and asteroids and dust that you could combine. But you also have about a tenth of the stellar mass inside of a galaxy in the form of gas, which is tricky to gather. The easiest way is probably just to wait until it cools off and turns into stars and then grab it, or maybe grab it after it has become stars. But there is even more gas between the galaxies. And this is gas that might actually be lost forever because while some of it is falling into galaxies because of gravity, a lot of it is just falling out between the galaxy clusters. And as the expansion of the universe accelerates, it's going to be lost forever. And of course, most people today know. And then there is dark matter, which is kind of 5 times as common as our kind of matter. Now, the really interesting question is, can you use dark matter for anything? Obviously, it can sit there and create a gravity well. So there are some interesting use of that. But it's much less clear that dark matter can be used to build anything. Can you do information processing in dark matter? That seems very doubtful, mostly because we don't know what it is. But the standard models of dark matter say that it consists of weakly interacting particles, WIMPs. These particles fly not just straight through normal matter, but it also doesn't interact much with itself, which means that you can't really make a good computer out of dark matter as far as we understand it. It could be that there are interacting forms of dark matter. Maybe a small fraction can form dark matter chemistry and do all sorts of interesting things. We don't know yet, but given the distribution, it looks like shapeless blobs as far as we can tell. So it might just be useful in form of mass. In theory, you can feed this mass into process that convert matter to energy, and haha, now we have an enormous amount of energy. And then, of course, there is the dark energy, which seems even less useful because it's probably a constant energy that just exists in space time. So that's the stuff we can play around with here. Now, how much of that can we actually grab? Well, there is a limit on how far we can travel in space, which is about 14.5 billion light years or 4.9 gigaparsecs. And the reason is the expansion of the universe. So even if we rush right now to a spacecraft that is moving at the speed of light, there are galaxies we can see that actually will never be reachable because while we're moving there at the speed of light, they're accelerating away from us because of expansion is making everything further apart. And this is speeding up, which means that there is an event horizon that actually indicates this beyond this point, you can't get that. As a parenthesis, normally we talk about event horizons in the case of black holes. But really, in general relativity, event horizons indicate that this is a surface of some kind that if you're on one side, you can't get to the other
Mm.
side. So the black hole event horizon is kind of the famous point of no return. But here we are in a kind of inside out event horizon. We can't get out. And every point in the universe is surrounded by its own event horizon which right now are billions of light years away, but we're slowly closing in because of accelerating expansion. Eventually, this means that galaxy clusters are going to be moved apart and become unreachable from each other. And that means that the only thing that gets left is going to be galaxy clusters or maybe some superclusters. So if we wait too long to grab the cosmic endowment, we're not going to get it. On the other hand, this is a relatively slow process. So if we just sit around fiddling our thumbs for a million or a billion years, we don't lose that much. But still, we're
Proportionally speaking. Oh,
yeah,
sorry about
comparatively
that.
speaking.
Yeah.
But yeah, we are literally losing galaxies, a galaxy per year or something like that.
Yeah.
Now, the tricky part here is if we just went out and grabbed everything within 14.5 billion light years, that's an enormous amount of mass, something like 10 to the 52 kilograms. And I have no way of visualizing how much that is. I can see the number, I can calculate it. I have no sense of it. It's kind of useful to know that Earth has a mass of order of 10 to the 24, 10 to the 25 kilograms. So this is not just kind of the square of Earth's mass or the
Mm.
cube of Earth. It's way bigger than that. The sun has a mass of 10 to the 30 kilograms, roughly speaking. That's still more than 20 orders of magnitude away. That's like the difference between me and an atom inside
So
this.
the difference of factor of trillions, or
Yes.
billions of trillions,
Yeah.
10 to the
So
12 is, yeah.
literally, we can grab billions of galaxies if we move at light speed. Now, if we move at half light speed, we can only go about half as far, and we get an eighth of that, so we get much less. So depending on how fast you move over intergalactic distances, that's going to rather strongly determine how much of this stuff you get. Now, how much of it you want to get is, of course, another big question because it all depends again on value.
Mm.
What is it worth to you? What do you want to use it for? If you just want to go explore strange new worlds and find new life, you want to go very far, but you also want to be able to report back to Star Control what you found. If you want to convert it all to paperclip or the computer is running happiness, then you want to also go very far, but you're only interested in the baryonic matter that can be turned into proper paperclips or happy computers. If you, on the other hand, want to just build your super civilization and go around the crystal pillars in your toga and think very wise post-human thoughts, now you might want to bring in the galaxies nearby to form a gigantic cluster that doesn't get separated. But you don't really want to go billions of light years away because you can't actually bring anything useful back from there. And of course, some people might say, yeah, actually, I'm pretty happy here. I just want to sit here and enjoy tea here in my little village and watch my friends and, who are totally normal humans with no weird transhuman or post-human enhancement play cricket while I talk with the vicar. So there is a lot of possible futures and goals, and they all require slightly different takes on it. And we also have very different views on what the real cosmic endowment is.
Let me just find, you did a paper with a whole bunch of other people working in very, various similar fields about like long-term future trajectories.
Yeah, so that was the result of me being a guest professor back in Sweden a few years back at the Gothenburg Center for Advanced Studies.
Mm.
And basically, my job was to be the excuse to bring awesome people together who could actually do the real work by thinking and talking. So we were running a seminar a day talking about everything, and then they wrote papers about it. And this paper is really about what trajectories are possible. And I think we can say right now we're on kind of this upward exponential trajectory. More people, more information, more wealth, a lot of stuff. But of course, it could just crash. Things could go badly wrong. Much of this work we did in Gothenburg was about reducing existential risk. You can also imagine that, okay, we're peaking, and then we go kind of crash back, and then we are living kind of a primitive civilization for hundreds of thousands of years until we die out for some natural cause. Or you could imagine that, okay, this is the best there is. We basically created the perfect civilization, and now we're keeping on doing this. We're going to get parking tickets and argue about the NHS for millions and millions of years. That also sounds rather weird. Or you can imagine that it continues. You will have a singularity and go off and becomes something weird and post-human we can't really speak of. In the paper, we were also talking about kind of going to space. That was one of the trajectories. I think that one and the post-human one are fairly closely interlinked because living in space as a squishy biological human adapted to living on Earth's surface is not that easy. You
Mm.
need to build a life support system that's ridiculously good. I think it's totally doable. It might even be worth doing, but it's so much harder than if you actually could just download yourself into a body suitable for that particular environment. And when you need another body, well, you just beam over to that one. But the trajectory paper was mostly pointing out that we have this trajectory choice. We can talk about what increases and decreases the chances of ending up in one. So, for example, the one where we kind of keep at this level, that seems very weird when you start thinking about it. It's not just that we need to be perfectly sustainable, but we also need to avoid evolving. And there is genetic selection happening at this moment, not just in the sense that people select who they want to have kids with, but also young people getting killed by car accidents. If cars behave like they do for a million years, eventually we are going to evolve defenses and evolve traffic safe behaviors. But most likely, of course, we would say, yeah, but human culture changes. We're probably going to break out in one direction or another. So I think in general, what is important is figuring out what happens along these trajectories or the ways of avoiding going along the really bad ones. And can we say something about where the really good ones actually go off so we can cut to the chase and start preparing for that?
Yeah, so that actually leads really nicely into the next question I had. Bravo. It sometimes looks like we've planned this. We really haven't.
It's total improvisation.
Um, so, kind of how do we go about reaching up the Kardashev scale? You know, if we wanted to start bootstrapping ourselves into a multi-planetary, multi-solar system, you know, multi-galaxy civilization, how do we go about that?
Mm, So I think it's useful to reason backwards. So assume that we have become a multiplanetary civilization. What must we have achieved before that? The most obvious thing is, well, some form of space flight. That's kind of done. I actually got a portrait of Yuri Gagarin here across the room. He kind of got there. Yep. Uh, check one. We need to make this work really well. So we need to improve, of course, our rockets, or maybe find another way of getting to space, like orbital elevators. If we have a good enough nanotechnology, you can actually have a cable from orbit down to ground. There are issues here. I've been arguing with nanotechnologies about how likely it is to work for Earth, but it might definitely work for Mars and the Moon. The problem at Earth is that the high gravity actually means that the tension is so big that if individual molecules break inside the cable, they're going to recoil at the speed of sound and cause a lot of damage. And avoiding those cascades seems to be an engineering challenge.
Yeah, I know that currently graphene production has a lot of problems with getting consistent strands. Um, who have you been talking to about this?
Well, mostly Eric Drexler, of
Of
course,
course,
because
I
he knows
suspected.
everybody. And he's also very good at pointing out what the fundamental problem is. But we're
Mm,
also the gentleman at the British Interplanetary Society, which is an
okay.
awesome organization.
Yeah, they do a lot of
Well,
very cool stuff.
yep. But in general, I like the idea of taking an elevator to orbit because that way you're not wasting a lot of reaction mass by just burning fuel and throwing it out behind you. It's such an inefficient way of getting anywhere. Getting around inside the solar system would be, of course, helped by better rockets too.
Mm.
So I have some other online friends who are all into nuclear propulsion, which is probably what you want to do if you want to get there in a hurry. The big problems of becoming multiplanetary, at least if you think that Mars is the first planet you want to go to, is that it takes kind of a year and a half to get to Mars from Earth if you follow a typical transit orbit. Those are the ones that use the least fuel. Now, if you had a really powerful nuclear propulsion system, you could actually speed things up, and your astronauts don't have to play board games for too many months. The
So,
problem is, of course,
oh, sorry, just to interject for those who aren't familiar, I highly recommend looking up Project Orion. It's super, super cool. We won't get too distracted from it now, but essentially the idea is you drop nukes out of like actual nuclear bombs out of the back of your spaceship, have a huge steel or iron pusher plate that absorbs the impact and sends you shooting up into the stars. If we ever need to get off Earth to like take all of our best and brightest away as civilization is collapsing, this is how we do it.
Yeah,
Sorry, you were saying,
except that
Anders.
you need to have a very reliable system with nukes. There are some engineering challenges involved which are really tricky. And for some reason, even the 1950s and 60s Americans felt like this is a little bit too much. That's saying something.
Yeah.
And incidentally, as a side effect of some of the calculations, they also realized that if you just detonate small hydrogen bombs underground in a chamber, you get a lot of heat down there. So you can just run a standard geothermal plant, and this is actually a form of fusion that we can build today. It might even be slightly cost effective compared to some of the more expensive nuclear power plants, except I think the PR budget will have to be enormous to make people accept this. So, yeah, Project Pacer, as it's called, is probably not going to go very far. But the kind of nuclear propulsion I was talking about is based on other approaches. So
All
basically, you
right.
have a nuclear reactor that heats some reaction mass, which can be almost anything. Normally when we talk about rocket fuel, we're thinking about something that reacts, becomes very hot, expands as gas, and then you blow it out behind you. Now, this does two jobs. On one hand, you want something with a lot of energy, so you get mass moving fast, but you also want a lot of heavy mass going backwards. That's really the principle for a rocket. The fundamental problem here is, of course, chemical reactions can only pack that much oomph. So the classic methods of burning the various hydrocarbons and oxygen, yeah, it's tricky. Oxygen and hydrogen, now that's much better, except that the liquid hydrogen is a really tricky material to work with. So many engineers are really very happy to avoid that. And so the SpaceX people have been interested in using methane, for example, which is much more well behaved.
And
So
pretty available across the universe, relatively
yes,
easy to
so
get.
that's another problem because the fundamental thing about settling space is that it's expensive to move stuff over there. So if you can use things that you get locally, you can do enormous savings. So in situ resource utilization is the fancy term for this. And many people have noticed that Mars at least has an atmosphere with carbon dioxide. And there are processes where you can kind of take water and carbon dioxide and react them and get methane, and then you use that methane as rocket fuel. This takes a while because the Martian atmosphere is pretty thin. But you can imagine landing a device on Mars and having it sit there for a few months or years, kind of filling tanks. So when you arrive and you want to be able to get away in a hurry, you can just take the pre-filled tanks. And that gets to the other requirement for actually setting space. We probably need a fair bit more automation. So right now, the automation in space mostly consists of astronauts using remote grippers or cleverly constructed things. We have a Canada arm on the International Space Station. That's about it. And of course, we have a lot of endearing rovers moving around on Mars and a few other planets. And let's face it, a lot of deep space probes are also, in some sense, robots, although they're mostly robots pointing cameras and sensors at different things. We need robots that actually build stuff, move stuff, and do much more. And what you need is both some form of mining of local resources, the ways of doing manufacturing, and then, of course, automation that can allow you to do the mining, do the manufacturing, and do useful things. So if you think about the perhaps most reasonable first step of building a lunar base, right now we would need to launch a lot of stuff from Earth, spending an enormous amount of fuel, even in a very fuel efficient rocket, lifting it out of our gravity well at an enormous cost and sending it over to the moon. Once you're outside the immediate vicinity of Earth, of course, you can get to most parts of the solar system. The difference in velocity is not that big. But now putting everything on the moon, that's going to be horrendously expensive. So if you could take lunar regolith, the kind of the dusty surface of the moon, and put that in the furnace and extract stuff that's useful, you would save lots of resources. The most important thing on the moon is, of course, water in some of the dark craters near the South Pole, which also conveniently is close to a peak that is known as the peak of eternal light, because it's so high that actually you get sunlight on it all year around,
Hmm.
which is kind of useful if you want to put some solar panels there. Of course, I think nuclear power might also work well, except that you have, besides the PR problem, there is another interesting problem with nuclear power on the moon. Where do you put the waste heat? So normally on Earth, we rarely have that problem because it tends to convect away from warm buildings, or if you have a coolant fluid, you heat up an ocean or a lake. That might be locally ecologically problematic, or maybe really nice, because you can actually run a local ecosystem that's helped by that. Near the Forsmark nuclear power station in Sweden, they have a little test bay. There is a little archipelago of islands where they put the warm water from the reactor. And it turned out to be very good for the animal life because in winter it doesn't freeze over. So seals and relatively rare birds go there. They kind of enjoy that.
Oh, cool.
Yeah, so this is super convenient, but that's because we're surrounded by water and air. Now, if you're on the moon's surface, you're surrounded by vacuum. At that point, the way of getting rid of heat is black body radiation, heat radiation. The problem is, although that scales with the fourth power of the temperature of your radiator, it's still very much more inefficient than having air and nicely waft it away, or even better, water. So you need big coolant fins. This is also true for nuclear propulsion spacecraft. It's not just that you want to have a nuclear plant heating up your reaction mass and throw it backward. You need to keep stuff from melting, so you actually need radiators. So realistic sketches for nuclear powered spacecraft involve a lot of fins, not to steer by, but simply to radiate away a lot of heat. And again, you can get into lovely, lovely engineering questions about how to do this in the right way. Everything from just passive systems of copper wires over to hilarious systems where you have literally molten metal droplets falling and being captured on the other side, but to really maximize the amount of energy loss.
That sounds
But
very cool.
yeah, it is. But anyway, these are problems that are kind of standard engineering. It's tough problems, but it can be done. The really tricky thing that has not been demonstrated well yet is this automation. And the interesting part here is if we manage to do the kind of automation that would make it possible to make a lunar base in a convenient way, or setting up things before the arrival of humans on Mars, we would also have a pretty powerful tool for making stuff on Earth. So some people say, oh, we need to go to space to get all the resources because Earth is starving and we have too little of fill in whatever metal or element they're most concerned about. But in practice, if we can get it from space, we can probably actually get it on Earth too, using the same methods. And the Earth is so much nicer than the space in terms of our equipment, and our engineers survive much more easily. But once you have that automation, the fact that we can now actually have not just automated mining and recycling and manufacturing on Earth, and we have, of course, also to have the closed ecosystems, which means that agriculture and environmental impact also becomes rather manageable. It's still kind of worthwhile to go to space to reduce existential risk, to see what's there, or build things that actually don't work on Earth, like gigantic solar panels when you want that really serious energy. But it's worth recognizing that most business plans people have for explaining why we need to set the space don't make much sense, which is really annoying. I wish somebody had a brilliant business plan, but it's tricky. Right now, most of the uses of stuff you make in space is for space. So it's going to be a bootstrapping problem that's going to be tough, and that's going to take a while. So while Elon Musk is favoring the approach of a rich guy really wants to go to Mars because of his reasons, and he can pay for that, Jeff Bezos seems to want to go back to the 1970s vision of space industrialization Gerald O'Neill and others wanted, where you have solar and capture to get a lot of energy. You might be manufacturing stuff in microgravity, and you're building space habitats. Uh, I'm kind of wishing both of them the best of luck. I'm kind of hoping both of them succeeds. Uh, I'm noticing that Bezos might want to have something that actually pays for itself, while Musk is mostly doing his long-term project right now as his project, which is
Yeah.
great. If he changes his mind and decides to take up stamp collecting, Mars is getting into trouble. So we want to have things that are self-sustaining, which eventually they will be. The good news is many of these technologies are probably coming down exponentially in price over time. The bad news is many of these technologies are kind of having scary applications, which means that the risk on Earth might be going up exponentially in time. So there is some point where I definitely want to get off this planet.
Yeah, I mean, it being my specialist area, the Neuralink stuff is both fascinating and very cool and exciting and a little bit terrifying. Um, yeah, I'm hoping that there are effective safeguards and appropriate cybersecurity measures in particular in place when it comes to, widespread integration of our brains with computers.
Yeah, and this goes for practically every technology. So in my book, I'm arguing that any sufficient advanced technology is indistinguishable from a weapon. And the reason for that is that if you have an advanced technology, it's able to change things a lot. Unfortunately, changing things a lot, that quite often involves changing things in ways we don't approve of or don't survive. Um, so this is, for example, a rocket and a satellite. Well, that's also kind of a missile. It's the same thing. Missiles are just satellites that have Earth intersecting orbits and a payload that survives
Well,
re-entry.
given the order that they were developed in, it's more like satellites are just missiles that don't come down, because
Yeah, yeah.
all of the historical development was initially focused on, lofting a nuke over to the Soviet Union, and hey, we can also go stand on the moon. Wouldn't that be cool?
Yeah, and then people who wanted to go to space, like Sergei Korolev, used the missile argument to get space done, which I
Yeah.
think more power to him. I think we should be very grateful for people like him and Goddard and others. Uh, but the problem is, of course, this goes for almost any technology. If you have self-replicating mining robots, brilliant. You can build your moon base or Mars base, or you can dig up a desert and make missiles out of the equipment you build there. So there are interesting problems here about coordination, safety, etc. We probably need over the next few years to figure out actually how do we handle economic activities in space, because right now it's not working. It's not just America and China yelling at each other about re-entry of pretty big rocket pieces, and the problem of keeping various orbits clean from fragments and space dirt. We are going to get even more trouble, of course, when people actually are trying to grab the economic value, including when somebody wants to bring down 1,000 tons of platinum we somehow got from an asteroid onto Earth. That's also, yeah, you don't want that to miss the intended target and land on the wrong place.
Very
So
expensive disaster.
very expensive. And you also have interesting issues like the various conventions we have about sterilizing space probes when they go to areas that might have life, like Mars. Uh, they're very, very rigorous. And a lot of the asteroid mining community thinks, look, we don't expect to find anything on our asteroids. We don't need to sterilize stuff. That's just making everything expensive and complicated. And the scientists across the room said, no, better safe than sorry. We have a business to run here. You can do that with Mars. We don't need Mars, but we want it for asteroids. And then they get into all sorts of interesting quarrels, especially when some scientists actually suggest that maybe we should look for bacteria on asteroids. There is a very fun possibility that during the formation of the solar system, some of the planetesimals that were forming might have regions that were surprisingly big where liquid water could have existed at the time. So if panspermia is true, that were actually spores for microorganisms around in space, there might actually have been bacteria in the planetesimals, and maybe one could find them in asteroids.
Yeah, it's
This is,
certainly
of
not
course, not
impossible.
popular among the asteroid mining community.
Understandably.
Yeah, but getting back to the
Yeah.
cosmic endowment. So becoming multiplanetary, as I said, you need to solve the basic moving around problem. That's more or less solved, but we could get much better at it. The space mining, manufacturing, recycling, and the life support things need to be demonstrated. On Earth, we have demonstrated closed ecosystem. We need to try that out in space. We also, if we want to have squishy humans in space, we need to do a lot of better radiation protection because space is not a nice environment from a radiation standpoint. You can try to upgrade people, give them a lot of antioxidants, maybe trying to splice in some DNA repair genes from the radiodurans bacterium, but it seems tricky. It's probably more that have a lot of water tanks around the astronauts in the spacecraft. And then, of course, there is the gravity issue, which on one level is kind of pointless. We know humans can survive without gravity. The question is, can humans thrive and reproduce without gravity? We don't know yet. And we probably don't want to find out the hard way that we can't. Making artificial gravity, of course, everybody knows these torus-shaped space station. They're a kind of visual cliche going back to the 1920s or something like that. They're actually a really stupid way of doing it because if you build half of it, it's useless. So you need to build the entire station, otherwise you can't actually use it. On the other hand, if you have your spacecraft and a counterweight, and connect them with a cable, then we can rotate around. I'm not doing a great job here,
Mm.
but you can imagine this rotation. Then you get 1G, and you just need to have a strong cable.
Yeah.
That's way more doable. You can have a really long cable, which means that the Coriolis force doesn't get too intense. Because if you rotate it really fast, you're going to get all these curveball effects when you move around, and that's no fun.
Also, presumably you want a I'm imagining here essentially two kind of skyscraper-like, obviously sealed off and surrounded with protection. But so you've got floors going up towards the center, um, with correspondingly gradually a bit less gravity on each floor, and
Yeah.
then presumably some kind of central station so you can take advantage of microgravity and easy docking and so forth.
Exactly. And you can arrange this in a lot of ways. You can imagine this being a temporary thing, like if you want to go to Mars, it's going to take you a few months. Then you have a spacecraft that first launches normally, and then you detach half of it and they start rotating. And once you need to do a maneuver, then you wheel in the things and stop having gravity. Or you might want to make permanent stations, maybe string a lot of them along an axis or something. So that seems to be doable. Basically, you can argue that there is a kind of minimum viable product for settling the solar system. And it's an amazingly crappy form of settling the solar system. Imagine something like the International Space Station, but equipped with autonomous systems that allow you to grab an asteroid, take the part of it, melt it, and turn it into pieces of a space station. It needs to be self-supporting with food, but that could be just algae and yeast gruel, stuff humans can subsist
Lovely.
on. Yeah, really lovely.
Actually, with
And
artificial flavorings and stuff, you can probably make that not bad.
yeah, or you select the people who think Soylent is the best thing ever. And actually, this is the trick. You select a lot of really peculiar people who think that mining asteroids and eating Soylent all the time, that's great, and I don't care about nature.
Just go to Silicon Valley, you'll find plenty of them.
Yeah, yes,
Or
that's a
Oxford.
fun part. I know people like this, and we can use them to fill this up. And then, assuming everything in life works out normally, you would end up after a while that they have built another station, and they also have a bunch of kids that decide as teenagers to move out because their parents are really annoying, so they move into our station. If you can do this so it reliably succeeds in reproducing itself, even if it's a generation time of, let's say, 25 years, in that case, you have exponential growth, and eventually you end up with the solar system overrun with these space stations and soylent eating people. They're a rather peculiar offshoot of humanity. This is probably the most low tech way of settling the solar system. I'm kind of hoping that we get something like the nice concept drawings from the 1970s, where it all looks like some kind of Bay Area suburbia, but rotating in space, or something even more interesting and post human. But I think that the ISS with Soylent is probably the minimum viable thing. We know roughly where we are and what we need to solve to get there. And that seems to be something that could be done in a few decades if we're kind of working on it. It's not that impossible project. Then, of course, we can start scaling things up. We already started on our own Dyson sphere in a sense by having a few satellites with solar panels in orbit around the sun. If we just keep on adding more and more, eventually we do end up englobing the sun. If we keep the orbits in shape, of course. If we start colliding, we're going to get a dust cloud and the biggest Kessler cascade ever, and then we kind of wrecked that part of the solar system and have to wait a million years until the dust cloud coalesces into a planet or something like that. Don't do that.
So, just for people who don't know, a Kessler cascade is otherwise known as a collision cascade, is where you get lots of objects in orbit, one fragments or multiple fragment, and start bashing into each other, causing further fragmentations, potentially shutting us off from a whole orbital sphere shell for quite a long time. Um, it's worse
Yeah,
the
and this
higher in
is a
orbit it
reason why
takes
we need
place.
traffic control in space and figuring out a way of making sure that the anti-satellite weapons don't get deployed too easily or accidentally.
Yeah.
Uh, so one of the
Uh,
interesting things about space is that it's very it's a dangerous place because stuff move at very high velocity relative to each other, literally kilometers per second, which means that very fast on a rifle bullet, which means collisions. Ooh, that's not good. Um, so on one level, space is very, very hard. But once you found ways of thriving there, that might take a while, then there is a lot of it. Once you have a system that can take asteroids and slowly turn them into habitats or other things that you like, suddenly you have a lot of it. The asteroid belt is big. Still, the total massive asteroid belt is still corresponds to just the upper few kilometers of Earth. So eventually, if once you turn the asteroid belt into habitats or solar collectors or spacecraft, you might start looking at other planets, or first small moons and then other planets. And at this point, of course, people start getting a bit antsy when you start talking about disassembling Mercury, for example.
you have an excellent talk on this, Emily.
Yeah, so we actually wanted to talk in our paper about settling the entire in the universe. But how do you send space probes that far? You need a lot of kinetic energy. You need to get that from something. Oh, we need a Dyson sphere. So part of the paper is looking at if you put solar panels on Mercury, use them to power robots, mining stuff to build more solar panels, more robots, and also send solar panels into orbit. How long does it take to disassemble the planet? And given some fairly mild assumptions, we found that it takes about 40 years. At first, nothing seems to happen. Slowly, the panels get bigger and bigger, but now you have more and more power to do more and more mining. And eventually, Mercury is totally covered. At that point, you need to start putting panels in space and beaming energy in. And you actually have some very interesting cooling problems. So the last phases, they happened in the last few years. So up until that point, Mercury has looked just like it's getting industrialized. And then suddenly, over a span of weeks and months, it gets turned into a cloud of solar panels. That's, of course, the magic of exponential growth. And there is a lot of interesting questions here about how one can control this, how one can ensure that robots building new robots don't accidentally mutate, to giving rise to unwanted artificial evolution. The answer is error correcting codes that can be made very, very resilient. But you probably also want to think about the computer security so nobody hijacks that thing and sends the whole swarm off against you or does something that you don't like.
Including potentially the AI controlling it. So this a question that we've just gotten in from chat. Is it even worth discussing these types of detail if you take into account that in the future that this will be possible? Superintelligent AI will probably already exist and be able to think of a way more advanced way of doing the same thing.
Well, a lot of this is probably going to be like Victorian engineers thinking about going to the moon and then suggesting cannons or the space railways. So that's in itself relatively pointless. But we can use these kind of arguments to study limits on what's possible. My approach is very much to look at the simplest and dumbest way of doing it and showing that even this simple thing can achieve that. Of course, the super AI will immediately come up with the counterpart to the iPhone or something like that. The really fancy and elegant way of disassembling planets. It only takes five transistors and a radio antenna to do. It's very, very neat and elegant. None of those robots and solar panels. However, I can still learn a lot of things by showing, okay, I can disassemble planets in at least 40 years. I know roughly the time scale these assumptions lead to. So we can be fairly certain that we can do it slower than that. Maybe it's possible to do super fast with that super intelligent trick. So this is generally what I'm trying to figure out. Where does the limits of even fairly simple technology allow us to go? So I've been describing ways of industrializing and essentially transform the whole solar system using technology that's not ridiculously different from what we currently have. And you don't necessarily need to have super AI to run these robots. They probably need to be on the order of a dog, or maybe one of the robot dogs from Boston Dynamics. They need to move things around in an effective way, sometimes notice that something is wrong, maybe sometimes call home to get advice. They don't need to be that smart. They don't need to discuss Aristotle between putting up solar panels. But generally, it seems like reorganizing a solar system that requires technology that we can conceivably get within the century. It might take a bit longer to actually reorganize the solar system, and we might definitely want to think carefully before unleashing these technologies, because otherwise we could make pretty grand mess of things. But that's of course the first start on the cosmic endowment. It's one thing to kind of have your own affairs on your planet in order, or getting the energy from the sun, and now you're on the level, not just level one Kardashev civilization, but a level two. That's kind of fancy. You got 10 to the 26 watts of power that you can use to power interesting things like spacecraft, giving them velocity to go to other stars, or engineering, or computers, or habitats, or lasers against your enemies, or just using the Dyson sphere as a very big telescope to see where do I want to go next in the universe.
So I think that was an interesting question because, as you say, it's really about that providing proof of concept and imagining what we can do with the kind of very bare minimum of tech, um, and finding out that with the things not even uh, far in the future, but kind of technology that we either have today or could pretty much be guaranteed to have in 5-10 years.
Or even had a long time ago. One calculation I have in my book is a steampunk Dyson sphere. Instead of trying to do anything fancy with photovoltaics, just imagine that you have polished metal, focusing sunlight on black boilers, heating up water into steam, running turbines. Uh, and yep, it's way less effective than many other possible designs, but that's kind of a Dyson sphere. I can imagine Islamabad Brunel standing around on some command bridge with his cigar and probably pulling some brass levers to run. That's
Oh,
kind of
that's brilliant.
physically possible.
Which raises a fascinating question of what kind of civilizations we might end up encountering, who, really rushed spaceflight but didn't advance anything else. And
Yeah. So the ordering of technologies is something that I'm actually trying to write a serious paper about, because they're both good opportunities for making the world safer this way, uh, by getting safe making technologies done before the dangerous ones. And there's a profound question about what technologies require other technologies. In computer games, we have tech trees where you need to research certain technologies to get access to other ones. They are based on various assumptions about our history, which are probably not always true, but sometimes somewhat recent. It's less clear that we can talk about that for the future. So, could you imagine a civilization that is at our level of advancement but don't have good medicine, for example? And I think the answer is up to a point. You can imagine some parts of medicine not being very well developed, but if you actually don't have enough antibiotics and vaccinations, you actually can't run a big enough civilization because you
basic
get
germ
inflamed all
theory
the
and
time.
hygiene practices, yeah, that
Yeah,
seems pretty critical.
exactly. You actually don't get enough people to run your big civilization. Now, on the other hand, nuclear weapons and rocketry, they don't have a necessary relationship. So Becquerel noticed that the rocks were kind of making his photographic plates go dark. Uh, that was kind of independent of any normal applied research. He was thinking about fluorescence and minerals, not really about anything else. And it was very independent of rocketry. So the line of research that led then the Curies to realize that there are intrinsic elements, and people realized, oh, nuclear decay and quantum mechanics and nuclear physics, and oh, chain reaction, Leo Szilard came up with when he was crossing the street at Russell Square. Uh, and then a few years later, mushroom clouds. That could probably have happened at a different part in time because it's fairly independent of rocketry. The rocketry involved a lot of chemical engineering, aerodynamics, and materials engineering. Now, in our timeline, what happened was rocketry turned out to be fairly useful with conventional weapons and got super useful with nuclear weapons. So, nuclear weapons helped drive rocketry to become very powerful. But you could imagine a world where actually the Becquerel guy never noticed that the photographic plates were darkened, and we discovered essentially nuclear physics a few decades later. At that point, we would have had rocketry for a long while. We might have discovered the various forms of radiation the hard way by having our astronauts getting mysteriously sick whenever we went into space. So that seems to have a lot of leeway. Now, what other linkages are there? Well, for example, if you can live in space, you would need certain forms of automation and energy collection, etc. So you would be fairly autonomous. You would also have ability to move these autonomous systems to other places in your solar system. So if you could just bring one of them to yet another solar system, you could settle there. So there, the main question is, can you either send people fast enough so they survive the trip, or freeze them if that's possible, or send some robot device over and build a habitat, and maybe even people at the destination. Or even, and this is one of my favorite ideas from Freeman Dyson, that you have people settling objects out in the Kuiper belt and Oort cloud in the outer part of the solar system. So you have these big balls of ice and, well, gunk. It's the lines that make them reddish. You melt ice, and from that you can distill out deuterium. So if you have fusion reactors, you can live a really good life here. You
Mm.
probably need nanotechnology to take that organic gunk and turn it into plastic and houses and fertilizer and people. But if you have fusion and good enough nanotechnology, or maybe even biotechnology, then you can live out there. You can't use solar power, you can't use fission because there is not that much uranium out there and you're too far away from the sun. You would need ridiculously large mirrors to concentrate sunlight on solar panels. That's probably not worth it. But each of these objects out there could sustain you for hundreds of thousands of years. And since you actually have fusion reactor and an awful lot of ice and water you don't really care about, you can use that to slowly push around. So when you started to run out, you sidle up to the next object and move to that one. And then you can imagine migration among these objects. They're light weeks and light months apart. But if you have a culture that spreads there very, very slowly, it's going to diffuse over to other solar systems. It turns out that within a few billion years, they're probably going to have settled the entire Milky Way. It might be that they never bother with the inner part of the solar systems because all sensible life, of course, lives out in the outer darkness. The funniest problem is that the deuterium is a non-renewable resource. In about 4 billion years, I estimated that they might actually start running out of deuterium, at which point, in desperation, they might have to settle the stars and planets.
A mad scramble for the inner systems.
Yeah, yeah. Although the mad scramble happens, of course, over almost geological timescales. So there are different ways of getting around the interstellar distances. This is the very slow way. Many people talk about generation starships, and I don't think that actually has a good chance of working.
Mm.
Because the problem is, a normal starship, if you imagine having people on board, it needs to be really big. And then you have a very costly rocket equation telling you how much fuel you need. And oh dear, that's not nice at all. Now, if you go slower, you need less fuel. But now you need a bigger crew compartment because now you want generations to live there. So now you still need a lot more fuel. So when you start doing the calculations, I never got myself convinced that it made sense to have a generation starship. But I think it makes sense to have societies and habitats that are nomadic. But I don't think it actually, if you want to get from A to B in 10 generations,
Mm.
when you still have a costly spacecraft. So in that case, I would go for something small and fast and automated with nanotechnology instead. Of course, if you want to go really fast, now you have a problem that now you're going to be slamming into stuff. As soon as you start to get into relativistic velocities, micrometeorites, which are nasty if you're in a solar system, now they become relativistic projectiles. And the interstellar hydrogen, which normally is just vacuum from our perspective, is started to turn into a proton beam, which is not very good for most electronics. You need to work rather hard on resiliency here.
Yeah, you're going to need some serious radiation shielding and error correction on top of that to
Yeah,
not have terrible value drift in your AIs controlling the whole thing.
not necessarily. So I think people underestimate how much you can actually make error correction work well. It turns out that I think it's about a factor of 7 or 9 redundancy that allows, if you imagine self-replicating probes that go on turning matter into copies of itself, and only the latest probe goes and makes a copy, and then it takes all the matter in the accessible universe and makes probes of this. It's going to take a very long time. I think 7 or 9 times redundancy is enough to ensure that there had not been any mutation when they're finished in converting the universe into probes.
Hmm.
This
Yeah,
is ridiculously good.
that's certainly not what my intuition would have been,
No.
but I suppose in biological evolution there is a lot of tolerance of mistakes in replication of errors, and
Oh yeah.
indeed some
So
systems that
biology
encourage it.
doesn't. Yeah, biology doesn't want to have too perfect replication because then you can't evolve anything and you
Mm.
become very vulnerable to a change in the environment. Probably there have existed a lot of species that had very low mutation rates, but we don't see them around. It seems like we get this tendency to move almost to the cliff's edge of having so much mutation that you get genetic meltdown. So there is a range that depends a little bit on how wild your environment is. Some bacteria, like the radiodurans bacteria, live in literally in nuclear environments
Mm.
like Chernobyl, and they have a lot of DNA repair going on because that gives them a nice ecological niche. Other bacteria get killed, so they get more nutrients. Other organisms actually have a lot of repair because they want to function. Whales, for example, since they have so many cells, they need to make sure that they don't get cancer there. So they have very strong cancer control systems. Now, the self-replicating probes, the low-level error correction is not much of a problem here. You can use off-the-shelf code, so you can use a little bit of clever programming to get interlocking things that ensures that the blueprints don't get corrupted. The real problem is if you want to give them slightly more clever behavior than just doing the same thing over. Now you might get a value alignment problem because now you have something that's essentially a small, simple mind. Doesn't have to be intelligent, but it certainly acts in different ways depending on experience. And now it might experience something you never thought of. So at this point, value alignment actually becomes important. So the whole discussion we have in the AI safety domain about value alignment and making robustly trustworthy robots really applies here. And they, especially if you want to let them out without control across the universe, you probably want to go through those the blueprints and check and verify and validate it really carefully, especially if they're really smart, because then they better be very friendly, super intelligent. So of course, once you achieve that, then you and you actually believe them very friendly, then you should probably just let them loose. The real problem is, of course, when you have a suspicion that maybe they're not friendly, they're just pretending to be, so you will let them loose.
Yeah, that's always a concern. It's something I touched on with Stuart Armstrong the other week, last week I think. We had a very interesting chat about how to keep them aligned and whether or not it's possible to stick them in a
Yeah.
box.
Yeah, and of course, settling the universe is the absolute opposite of being in the box. You want agents that can do things on a very grand scale. Now, in theory, you could imagine having a lockdown system. So maybe we have designed on our values, we lock it down, we have a self-replicating system that go off and implement this with no chance of ever doing anything different. That is, of course, problematic if we're wrong about our values. If we're really, really good and certain about our values, this might be the right thing to do. But there are also a lot of value systems that actually say that actually we want a fair bit of openness. Right now, I think the most sensible human value system says, I don't know everything there is to know about the universe or morality or myself. And it's a good thing that we can invent and try new things. And if you want to have that available, then you need systems that can carry that onward. It might be that you have a dumb system settling different solar systems and galaxies, and then a blossoming of humans and AIs doing whatever art and the culture and sports they come up with. But you still have a lot of risk from that if people go off in different directions and end up in conflict. There are even some people argue this is why we should never expand over these large distances because there might be terrible conflicts. I'm less worried about that. Not because I think necessarily everybody in the future is going to be nice, but it's relatively tricky to do conflicts over interstellar distances. One of the nice things is that the light speed limitations and the cumbersomeness of moving matter over long distances actually makes warfare tricky. Yeah, it's kind of frightening when you start to realize that Dyson spheres can direct lasers over hundreds of light years that can fry planets. And it's even more disturbing when you start realizing that the relativistic projectiles, they're kind of more powerful than antimatter if you give them enough speed. But on the other hand, they work really well only on targets you know where they are. If people move around, if people are a bit nomadic, you can't hit them over interstellar distances. You need to get up and close. And at this point, it's a bit unclear. It depends on some very deep questions about physics, actually, literally the physics of warfare. But it looks like as the scale goes up towards the cosmological scale, it gets harder and harder to actually do this kind of dynamical warfare that makes the attacker win. It might be that on the larger scales, the universe is very defense dominant, which means that actually, as soon as we expand on that level, it's kind of stupid just to have war. Similarly, in time, if we wait a few 100 billion years, the galaxy clusters get separated by exponential gulfs. At that point, if you don't have any neighbors, well, no problem. Now, the only thing you might worry about is civil warfare, but that's a separate problem, perhaps. So there are interesting intersections here between technical feasibility, like error correcting codes and AI safety, and how you set up these systems in order to avoid the evolution or get the right kind of evolution, and the value questions about what should we be doing with the universe.
Yeah.
Yeah, just to mention it, if you can expand across a galaxy with probes that move relatively fast, you can just do the same thing between galaxies. It's a factor of about a million longer distance between galaxies than between stars, but you basically probably have probes that are very good at error correction, don't they handle impacts rather well, and they can build an industrial base at the destination. There are kind of weird thresholds. To go to space, you need a rocket that can give you about 11 kilometers per second of velocity. And once you have that, you can take the solar system more or less. You don't need that much extra. Going to a next star, that's going to require something that works over long periods of time, or is very resilient, or have some other property. But once you can transport yourself about 7 or 8 light years, then you can jump from star to star to get most of the galaxy. You actually you don't need to be able to jump 100 light years in one go to get most of the galaxy, even though I think it's possible. And the next step is, well, if you can jump a few million light years, now you get most of the reachable universe. So there are a few steps here, and once you pass them, then an enormous domain opens up for you.
So I think that's a very interesting uh, idea, is the fact that, again, when we're talking about the kind of minimum viable product to achieve your goals, um, 7 or 8 light years, that's something that we could do with, currently sort of, if not right now, feasible present technology, or near future technology,
Yeah,
within one human lifespan.
yeah, it's worth remembering that the Voyager probes, we didn't aim them at any solar system, but we could have, which means that by 1970s technology is enough to send a lump of matter to another solar system. Not a functioning lump of matter, mind you. It's going to be a bit of a wreck when it arrives, but that was 1970s technology without even really trying. So I do think that the technology ceiling is not, we're not that far away from it. There is Project Starshot, which is a really interesting attempt using laser propelled light sails to send very small probes about the size of a stamp. It's a little microchip probe to nearby stars within a few decades. Basically, within the lifetime of Yuri Milner, who is bankrolling the whole thing. Incidentally, Yuri was, of course, named after Yuri Gagarin and is big on space, and both SETI and doing this. And the fun thing is, listening to the technical stuff, yeah, there are problems to be solved, but these are the kind of problems we roughly know how to do engineering on. It's not like, oh, and then magic happens, which was when people in the 1800s were talking about going to space. They had no clue on how to do it. In this case, yeah, we have a bunch of hard problems, but we actually roughly know what needs to be done to solve them. Now, the real problems are probably going to turn out to be very different from what people expect. When people started navigating around Earth's oceans, they started getting scurvy. That was not the obvious problem when Columbus and the others set off. They knew that they needed to handle storms and have enough food and handle mutinies. That was the obvious thing. Getting scurvy was kind of not on the list of problems. And then it was, of course, solved eventually, and the solution was also accidentally forgotten, but that's another story. But basically, people figured out eventually how to handle that problem. And this goes for many of the practical problems we're going to discover when trying to grab the cosmic endowment. On Skylab, they had a cupboard that should contain tools. And it worked really well when we tested it on Earth, and it totally failed in zero gravity because it turns out that the drawers were always jamming. That's kind of a small problem, but once they saw it happening, oh, we need to redesign it. And that's going to happen for an awful lot of stuff. As long as space is super expensive and you need to be super careful and plan everything ahead, you're going to have a very slow learning rate. If you get cheap space access, people are going to try a lot of stuff. A lot of things are going to fail in embarrassing ways. Just witness NASA's Mars rover that is trying to put a probe deep into the Martian soil and finding that it's actually too tough going. Soil is too packed. On Earth, that would have been easy to solve, but now it's rather far away. But we're learning from that. Now, if the threshold was lower, we would just send another probe with maybe a better soil drill or something like that. So getting the threshold down, I think, is the important thing for actually finding solution to the real weird problems.
I think part of that is potentially being more tolerant of, as a society, of mistakes in terms of, obviously things like the space shuttle disasters were, you know, terrible um, public kind of catastrophes, nightmares. But the number of people lost was still relatively small. And if we're going to scale up to many space flights, every year, every month, every week, then we're going to need to accept some level of occasionally rockets are going to blow up, occasionally they're going to slam into things they shouldn't. And while obviously each death is a real shame, if we're going to get that kind of level of technology, we're going to need to accept that sometimes it goes wrong in the same way as we accept road traffic collision deaths, which are in the hundreds of thousands worldwide a year, but the value we get from cars is so great that they're worthwhile. So I think
Yeah.
hopefully we'll see the same thing with space.
Yeah, so right now the statistical value of life is a bunch of millions of dollars. I think it's something like $7 or $9 million. That is kind of how much people are willing to spend to save an extra life by changing roads, etc. When
Yep.
you do the same calculation for safety measure for astronauts, it's in the order of trillions of dollars. Which, well, astronauts are really awesome people, but I think that shows that that factor or the extra, mm, do we really want to be that cautious?
Mm.
And I think the honest answer is, yeah, at first we might want to be that cautious, but we should be sending much more robots. Humans are really good and flexible, but they also require so much infrastructure. Actually, sending robots and having teleoperations might be a good way to actually test out things and do the mistakes that needs to be done early on. Because the real problem with fear of failure is also that you never try anything. And that's not just the fear of failure that the rockets blowing up and astronauts dying. It's also that, yeah, you're not even going to try that project because it might fail in an embarrassing way.
Mm.
And this is where I think we need to change our culture and actually accept a lot more. I think actually the current COVID pandemic has demonstrated that, yeah, sometimes people do realize in some jurisdiction and some bureaucracy that, oh, this is a crisis, I need to change the rules. There are other examples where they say, nope, the rules are rules, must never change them, even if people are dying. And I think we should, when the dust clears, kind of notice who was do the sensible thing, and then make sure do more things like that, and
Yeah,
then probably change the rules for the people who were rather rigid about the rules.
I think
At the same time, you want to have rigid rules about things that are very, very dangerous. If you can fry planets with your Dyson sphere, then you probably want to make sure that the targeting system is under control of sensible beings. If you can send relativistic probes over interstellar distances, make sure they don't point at planets.
yeah, and I think with regards to coronavirus, I would analogously like to see more use of, say, challenge studies, which involve some risk to consenting participants, but which potentially give us the kind of data that we can't get otherwise. And I think similarly in spaceflight, things like Musk's rockets that, based on my limited knowledge of aerospace, seem to be somewhat more risky than NASA's options. You know, if I were going on a space flight tomorrow, I'd probably rather take the NASA option than one of Musk's. But if I were paying, I'd probably rather go with Musk's because he's bringing them down to be, relatively speaking, incredibly cheap.
And also, he's learning very rapidly. I remember first hearing about trying to land on a barge, and I was kind of going, okay, that's just an
Yeah,
engineering
good
trick.
luck.
That's just silly. And then a bunch of YouTube clips of various crashes. Yeah, this is not going anywhere. Oh, that one almost worked. Oh, that worked. That worked. That worked. That worked. And now it's routine.
Yeah,
This goes for quite a lot of other technologies. So it's worth remembering that the rocket train engine, one of the earliest ones, on its kind of maiden journey, it ran over a member of parliament. And everybody agreed that's a horrible, terrible accident that should never happen again. But railways are really the future. This is great. Let's build more of them. While the Hindenburg disaster was essentially the end of Zeppelins. People decided, oh, that's not worth the risk. What was the difference? Well, the Zeppelins were basically luxury products. They were an expensive but convenient way for a very small number of people getting across the Atlantic. They didn't actually have that much everyday use. While the good burghers of Liverpool, they realized that actually that train really good for a lot of passengers and the industrial uses, and you could see how it could be integrated into a society and a culture. And I think the same thing is true for space. When you actually start to see it as integrated in your plans of everything, then it becomes much more reasonable to take the right kind of risks. So right now we're fairly dependent on our satellites to provide us with cable television and GPS, which might becoming much more important now, and many other things. Most of the time we're not aware of it, but I do think that as the infrastructure expands, it's going to get more integrated, and that might mean that we can also handle more setbacks. Right now, it's kind of expensive to crash a rocket, but that's usually the only way of learning how to do it well. We can run simulations, but then we need to have a few actual rocket crashes and compare to a simulated rocket crashes. So we still have the same problem.
absolutely. I think that's a very useful way of looking at it. And I mean, Musk got the Starlink project going up, and there's increasing talk of, you know, properly landing a base on the moon and trips to Mars, and ever increasing use of satellites for all kinds of communications. And the UK was even talking briefly about putting their own, you know, GLONASS GPS Galileo equivalent up. Although I think that's I think that's on the back burner now because they realise that would be a stupid project. But more generally, lots of positioning satellites, and yeah, it's the kind of thing that in the 80s, with the it was Challenger that blew up in the 80s, yeah. With the Challenger disaster, you can kind of see why that would create a hit. But I would hope now, if we do see a similar thing, that there would be a period of international mourning, and we would all be sad about the brave pioneers who sacrificed their lives, but we wouldn't shut down everything and cancel all the rocket launches.
However, I think the history of spaceflight also demonstrates that where we go with technology is also surprisingly dependent on culture, politics, economics. It's not at all as deterministic as many computer games make you think. Once you develop technology A and B, then you can make technology C, and then it continues along that line. In this case, uh, some setbacks, like the challenge disaster, meant that people stay away from it and become perfectionists. That actually slows down innovation tremendously. We saw the same thing in gene therapy when there was a tragic accident when a volunteer died
Yeah.
from gene therapy. And again, it was not done in the proper manner, and people retreated from it. And we probably lost at least a decade. But now
TGN
gene therapy is,
1412 monoclonal antibody as well.
yeah.
That was a big setback. Yeah.
In some sense, of course, it's a rational response. Something goes wrong, you withdraw, you try to learn from it. But typically, we withdraw too long, and investors go elsewhere. But what happens is eventually you learn, or you find other ways of doing it. Now, the problem with space, as I said, is I think becoming multiplanetary and multistellar and multigalactic is a really good thing. But it's worth noting that the technologies that enable that also enable you to live rather well on Earth. The main resource that exists in space is literally space. I actually think people underestimate how important distance is. Because if people in Muskwell on Mars get a new nasty virus, that's not much of a problem for Earth. You actually have a natural quarantine. It's kind of working from your home planet running here. Uh, Many threats tend to be relatively local, which means that actually spreading out is a good way of really increasing the viability of the entire population because it's now naturally separated. If you can settle asteroids, well, that means that you have communities that are autopotent. They can generate their own technology, etc. That is probably a tall order right now. We don't have a technology to make an industrial society. We need to find ways of packing it together with the right blueprints in a computer, 3D printers, or non-assembler, and AI and whatnot, so you can actually do this in an effective way. It might also be that that's never cost effective compared to having a big infrastructure, manufacturing asteroid bases or something like that. However, having those ultra-potent systems also means that a big disaster is unlikely to wreck all of civilization. So there's a value here, but the value is not necessarily the normal kind of economic value. It's more of a spillover thing. It's like people having holiday homes and boats, which is a great thing in the case of a disaster because you have an alternative place to live and an alternative way of moving around. They were, of course, not intended for that purpose, but that's quite a useful thing. So the tricky thing is, can we come up with short-term business models that drive space well enough so we can learn the tricky stuff? So we then can become multiplanetary. And then, of course, once we've well done that, we're not going to think about it. Just like we don't really think about the fact that we're multi-continental now as a species. Relatively few species exist on all continents. We're kind of unusual that we exist even on Antarctica. But that kind of cost a lot of effort. People can thrive in Antarctica mostly because there is agriculture and global communication in the rest of the world that can send food to Antarctica to the polar explorers and their base. But that's typically the way we construct things. We don't necessarily go just because it's economically necessary. We might be driven by a lot of really weird ideological or scientific reasons, but that seems to be what intelligent species probably do. And that's also why predicting where intelligent species go and what we do with the endowment of the universe is so much harder than predicting what a supernova or a bacterium is going to do.
Right, I have taken up quite a bit of your time. Um, so
It's no problem. It's so fun, but we can
well, if
always
you
keep on doing this coming weeks and so kind of keep on building.
yeah, I just don't want to take up too much of your time
Yeah,
right now. So if you're up for coming back on in a couple of weeks, we
of
can
course,
maybe
totally. I
uh,
mean, we only covered now settling the solar system and starting to set the galaxy. We haven't gotten around to how to move a galaxy or what we should be doing with the universe.
exactly. This is the next question on my list is kind of what should we do with it and why do we feel justified? And I was kind of
Yeah,
I
what's the
could ask
ethics
that
of
now, but that's going to take us another hour and
for
a half or
another
so.
year? Yes,
Absolutely. So thank you very much once again, Anders. As always, it's delightful. And
this
have you
is
got
so fun.
anything you'd like to plug? Anything any interesting projects of friends or anything?
Well, of course, I think generally looking into the breakthrough Starshot project and
Mm,
papers related to that, that's an awesome idea because
bring that back
uh,
up.
so they have Jerry Milner kind of set up this foundation, which is both giving out a prize to try to entice people to get involved in science and engineering and to inspire them, and making these interstellar probes. I think the original plan was to aim at Alpha Centauri, but now the Proxima system is starting to look really cool and hip, so that's probably the big target. Very interesting engineering challenges for people who want to get involved, not just like building giant lasers on ground to get, uh, make them move fast, which is a very fun optics problem and a laser physics and cooling problem, as well as a political problem. How do you convince everybody that this is not an anti-satellite weapon? How do you
Yeah.
control this system so it can't be used for bad purposes? Over to the light cells themselves. What kind of light cell? How do you make tiny space probes communicate as a constellation and so on? What is the amount of dust in space? One way is, of course, to send out the probes and just see what we hit. But maybe if it's too much, we need to do a redesign. There's so much going on here.
Cool. Well, I've got them up on screen. Yeah, this looks like a fascinating project. I'm gonna have to look into this properly, in depth. But backed by Yuri Milner, Stephen Hawking, Mark Zuckerberg, with
Yeah,
a
there are some slightly
whole
household
load of
names there.
Androyan, Carl Sagan's wife, and a whole bunch of important people there. Martin Rees, he's great. I love Martin Rees. Um, so yeah, looks really cool, and also it's not out for a while, but when Anders' book does come out, everyone should read it. I'm sure it's going to be amazing.
Yeah, the problem is, of course, I need to make it become shorter, not longer over time. I felt a surge of triumph yesterday when I realized this appendix must go. The conclusion is wrong. I'm going to get rid of almost 5 pages.
Sounds like a very academic problem to have.
Oh yes,
Yeah,
oh yes, and
editing down your
worrying
babies.
about footnotes. And do I refer to how do I refer to this principle? Which name is the appropriate one? Yeah. Well, more about that later.
Excellent. Um, right, well, I'm going to end the stream there. So, yep,
Yeah.
happy
Take care.
Wednesday, everyone, and I will see you